Okay, hello everyone. Welcome to this afternoon's set of talks. If you could just try and not just haunt the outsides of the middle aisle, just everyone on the outsides move in a little bit of their space, just so that if people are coming and going, they don't necessarily have to walk over people if they're coming in. Please, come on outside people, just move in a little bit. The middle is not that scary, I promise you. Smush, smush, smush. Remember, the middle is always the best part of a sandwich. You don't want to be the bread. Okay, our first talk today is by Carl Worth. Just a quick note, we will be taking questions at the end, and to get a question answered, you will need to raise your hand and wait for me to run around with the microphone. Okay, so our first talk is on measuring and improving OpenGL performance by Carl Worth. Carl has been fascinated with creating software since the precocious age of 10. He has been an active contributor to the free software community since 2000 in a variety of projects, most notably as the creator of both the Caro graphics library and the Not Much Mouse system. Currently, Carl is working for the Linux graphics team within Intel's Open Source Technology Center. So, welcome, Carl.
Thank you very much. I apologize about my voice. I managed to bring a cold bug with me to LCA, which is unfortunate. I knew my family had it before I left, and I was hoping I had left without getting it, but turns out I do have a cold. So, but everyone can hear me okay? Okay. I've been staying mute all day today, just trying to keep my voice a little bit. Okay, so I'm going to be, my talk is titled Measuring and Optimizing OpenGL Performance. There's kind of this funny problem with LCA submissions is that the call for papers comes out significantly in advance of us actually appearing to talk. So I'm actually going to be talking more about instrumenting and debugging OpenGL applications. But, you know, there is some performance-related things, and if the change of my title really discourages you, I won't be offended if you leave. So let me talk a little about who I am. I appreciate the introduction. I work for Intel OTC, and I say OTC because Intel has a fascination and a love with, I can't even say three-letter acronyms, I can only say TLAs. And so, you know, I feel a part of the Intel culture if I speak in as many acronyms as possible. So OTC does stand for Open Source Technology Center. Open source has to be hyphenated so that we can keep it a three-letter acronym. Four-letter acronyms just would not do at Intel. Within OTC, the team I'm on is working on free software Linux graphics drivers. This team came into existence in 2005 when Keith Packard came to work for Intel. It experienced rapid growth. The team doubled in its first year when Keith hired Eric Anholt as well. And so they're both back here. I don't know, a couple years or so later, the team doubled again when myself and Ian Romanek were hired. And we've probably gone through a couple, well, not a couple doublings since then, but we're probably about 16 people now. And most of what that team of 16 is working on is the OpenGL drivers, the implementation of OpenGL, because there's a lot of what it takes to make OpenGL work is not driver specific, and that's a wider open source project. It's not just contributed to by Intel. That project is known as Mesa, but our team at Intel is doing a large bulk of that work. Obviously, the drivers within Mesa for Intel graphics chips, and then kernel work to support that as well. So I want to talk a little bit about what a modern graphics driver is. If some people, I don't know if you've ever been to, I don't know, maybe an LCA tutorial on how to write your first kernel driver or something. You might have this notion of what it means to write a driver, and you might have some piece of hardware, and you go through the specifications, and it has these registers, and you poke values into those registers, and different values make it do different things, and that's really fun, and that's the level that a lot of drivers work at. It turns out that maybe graphics cards work like that once upon a time. At the time they did, I wasn't involved in graphics. And for today, graphics drivers don't work like that. We have a much more sophisticated thing going on. We have this graphics hardware, we have this graphics processing unit, this GPU, that really is a peer to the CPU. It's a fully programmable, multi-core, multi-execution unit device. It does its own hardware. It does its own scheduling within the hardware. So the CPU just gets to send a bunch of instructions to the GPU, and they'll get scheduled and run at some time, and you don't even know when, and don't have a lot of control over that. But even up at the application level at OpenGL, OpenGL provides to the users the ability to write programs. And what I mean is you're writing a C program or whatever language you're targeting OpenGL, but one of the API calls you have is to take a string of GLSL language, the GL shading language, and you pass that in to the OpenGL implementation. So it's almost like what it means to write a graphics driver today, to write an implementation of OpenGL. It's a project I like to think of it as similar in scope to what it is to write GCC for the CPU. We have to take this this high-level programming language, GLSL. We have to compile it. We have to turn it into instructions for this GPU, and then ship them off. And at some point, the team realized this and said, oh, we need a real compiler inside of Mesa. And we don't have one, and we don't know how to write one. We're not compiler experts. So we don't know any compiler experts, so I guess we better become compiler experts. As a team, I'm saying me because this isn't me. I'm not a compiler expert. I wrote the C preprocessor front end of the compiler, but nothing else. So the team went out, got a bunch of textbooks, and learned how to start writing a compiler. And it's been a lot of fun. We've learned a lot and realized how a lot of our initial implementation was wrong, and we're throwing as much of that out as we can, as fast as we can. So what are some of the unique challenges that happen if we're comparing GCC targeting the CPU to now OpenGL and the DLSL compiler targeting the GPU? What are some of the unique challenges? Well, the GPU doesn't give you much visibility into what's going on. When it hangs, it often will take down your entire system, so you can't even do anything. You don't have the ability to use a debugger, and some people don't believe in debuggers even for CPUs. But some of us would love the luxury that would come if we could sort of single step through the actual instructions being executed by the GPU, but that's not anything we have. That's a capability we just don't have. So when things go wrong, when things aren't working, it's often really hard to figure out what's happening and why things aren't working. So like I mentioned before, the growth in our team size over the last few years, and one of the things that has led to is a chance to step back and think about what we were doing. And here's a question. I'm going to talk about a transition that happened for me about a year and a half ago. So have you ever heard or thought or seen in your experience of this kind of question? It's where you say to yourself, one day when we're not so busy working to get all these features done by deadlines, if I could just take a break, I can write some cool programs that would help me be so much faster at writing features to meet the deadlines, right? And that's the situation our team was in for years. We were just coding as fast as we could, with as many people as we could, just to get stuff done. And we were realizing that a lot of what we were doing was inefficient, but we didn't have time to step back and to write. We said, well, if we had a tool that could do this, that could tell us these kinds of answers, that could give us this insight and guide us to where the priorities were to be working on, we could avoid wasting a lot of time. But we could never afford to waste the time to do that. And so that was the apparent situation we're stuck in. Well, about a year and a half ago, when I realized our team had gotten to be as big as it was, I said, look, I've heard this over and over in a lot of different situations where the engineers are saying, I wish I had this, but oh well, I'll just keep hacking away. I said, we need to dedicate some time and some effort into just writing the tools to help us do our job. And at about that time, I didn't invent the program API trace. We found the API trace. And so I want to give kudos to Jose Fonseca of VMware, who was the original author and maintainer of this program. And I've told I talked to a lot of people about what open source means, what free software means. And one of the points I like to make is that you don't have to, well, for one, you don't have to be a developer to get advantages from open source software. Right? Even my friend who's a dentist who always could never understand, he says, Carl, why do you always give away programs. You should be selling them on the Apple store or whatever it is. You could keep making $1 per program, and we could be rich. And he has a hard time understanding, but I said to him, I said, well, you would benefit from running free software, even if you never wrote a line of code yourself, because other people write that code for you, and they have the ability to approve it. And one of the things I told him, I've noticed again and again in my life, when I've sat down and thought of a really good idea, and I thought, oh, you know what, a program would be really great to have. Yeah, this is good. This is going to be a good program. I used to take that and immediately start coding up my idea. But sometime after I'd been running Debian for a while, I realized there's a much better thing to do. When I realized, oh, here's a program I wish I had. Instead of starting coding, I just start looking through app cache search and find that, oh yeah, someone else already wrote that program for me. And that's one of the magical things. You can just sort of, you have this mental magical power by just thinking of a program. It can exist and be on my program. And I love that. So we did that with the API trace. We kind of spec'd out. We said, if we had something that could, a layer that would sit in between the application and the OpenGL implementation, and it could capture all of the calls that were done, and then afterwards it could replay all of those calls, and then we could look at what it had done. That would be a really cool program. So as soon as we had specified sort of roughly what it was, we looked and we found, oh yeah, look, Jose's been working on this for the past 6 months, and it's right at the point where it's actually really useful. So that's what API trace does. It's a shim layer. It implements. It has entry points for every function in OpenGL, and there's a lot of them. It works at least on Linux with an LD preload and similar mechanisms on other operating systems, so that it gets all these function calls first. It can see all the data. It can record all of those to a file that it compresses up, and then it passes everything on down to OpenGL. So then, like I said, you can replay and analyze things. So I want to do a demo. I want to show you a little bit about how API trace works. But before I do, what do we know that every demo needs? We need rockets. I'm glad Keith and BDL are here. This slide was just for them. Well, no, we don't really need rockets. What we need is an artifact from the rockets. We need some of that smoke. But the smoke's only half the picture. We need smoke and mirrors. So here we go. So now we're ready to do our demo. I got me smoke in my mirrors. Let's see if this is going to work at all. There's a program. I think it might have been in this room. How many years ago, BDL, that your daughter gave a talk about Tux Racer? 2 rooms down. It was in this building several years ago, and there's this program called Tux Racer. Well, we could go in here and we could practice, and we could race ducks down the mountain. Okay, that's not really a demo because that's just Tux Racer. Tux Racer is annoying in that it didn't mess things up too badly. Okay, so it was changing video modes on me. All right, so now, instead of just running, why am I, well, it was something not working there. Hold on. Okay, nope. That's really frustrating. This is Pippin's fault. Why is left arrow not editing my thing? Okay, I'm gonna give this one more try, Pippin, and then I'm hitting tab to edit, and I'm hitting left arrow. Nope, it's not working. Okay. What's that? It worked this morning. It worked 5 minutes ago. It's been working all day. All right. I was just telling you how I loved this aspect of the slide program was that I didn't have to bring up terminals and type commands in them where nobody could see what I was typing. But anyway, the slide program's not working. So, no, can't even make the font bigger. What I'm typing here that you can't see on the screen because it's in a microscopic font is API trace ET racer. Looks like a lot of traces. Okay, so I'm running the same invocation of trace. I haven't modified the application at all. I've just said API trace in front of it. And now I come in, and the game plays about the same speed. It's maybe a little bit slower. My disk gets really busy, and it works just fine. And so you can imagine I don't know, maybe there's something interesting down the mountain. No, there's nothing interesting here. Okay, so that's good enough. I'm not very good at Tux Racer. I don't play this game. And quit. All right. So an artifact of having run API trace is now I have an etracer.trace. I got too many traces in there. File in this directory, and now I can replay it with this command: API trace replay etrace.trace. Let's see if this works today, Pippin. nothing's working. Okay, API trace, replay, eTracer, trace. Okay, so now, this time there's no hands, right? So API trace is loading. Oh, that's very sad.
.1.trace.
What's that?
So it says it's saved in eTrace.1.trace.
Yeah, okay, that makes more sense. Okay, so I tested one time too many before and left it in a file sitting around. Okay, so yeah, like I said, I'm not touching it, but we should see bugs take exactly the same path up the same hill, just like you saw before. Okay, so I did not too much smoke mirrors. That's actually replaying the same thing I just recorded. When we traced it, we have this file that collected all of the operations, and when we replayed it, it loaded the file and replayed them again. Okay, that was cool, but what's the point? Why would anyone care about doing that? What's that? How big's the file? How big's the file? We said we were going to take questions afterwards. No, I'm not even in the right directory. We'll look at that later. All right, it's pretty big though, relatively speaking. So there's probably, I've identified 5 different reasons why API trace is interesting. One is to actually capture bugs for bug reporting, bug communication. One's for debugging an application, doing conformance and performance testing, benchmarking, and performance profiling. So I would go through each one of these. That's really the outline of the rest of my talk, because it's 5 different use cases, and talk about this. The first one is bug capture. Now, that's a really ugly bug. But worse than, we have lots of nasty bugs in OpenGL and in our implementation. I think all of us do in our software. But worse than nasty bugs is nasty bug reports, right? These things that come in and you can't do anything about them. So here's an example of a really kind of nasty bug report. That's the flavor, the kind of thing we see a lot with Mesa and OpenGL. Someone starts off saying, well, okay, there's this rendering bug, okay. It's in this proprietary game I'm playing, and it's at least 7 gigabytes, and who knows how available it is and how expensive it is. And by the way, you have to play to the last level of the game before you can actually see the bug. So, I mean, I don't know, maybe I could use this as an excuse to just sit there and playing games, and when Dirk walks by my cubicle, I can say, no, really, I've got to find the bug. He says it's in the game somewhere, I'm going to find it. The point is, the OpenGL applications are huge, they're complicated, the environment to be able to replicate these bugs is really nasty. Sometimes it's almost impossible to be able to replicate everything. So with API trace, we have an easy answer for bug reports like this. And this has been, from the moment we started using it, this is what we see in Mozilla all the time as like a first comment back. We're like, great, you've got a bug, cool. Send us a trace, then we'll look at it. And that's just been an invaluable tool for us, because we actually get these traces instantly. We replay and we can see what the actual bug is. There's one problem with the, so I was complaining there about a 7 gigabyte game. Mike was asking how big the trace is. The trace might be several hundred megabytes still. So it's still pretty big, and that could be an issue. We'll talk more about what we're doing for that. Oh, we're talking about that right now. Okay, so you noticed when we replayed Tux Racer, the first thing you saw was the menus and going around and navigating around, and then the penguin actually gets to maybe the interesting thing that the bug report's about. Well, that's a bunch of wasted stuff. So when I first started playing with API trace, I said, yeah, we're getting these huge files in and they have too much information. Wouldn't it be nice if we could trim them down to just the things we actually want? And so I implemented this API trace trim feature. And I don't know. Oh, it's going to replay today. Okay, so here's a replay of a trace. This is called Neverwinter. This game is called Neverwinter Nights. And you see exactly the same thing I mentioned before. The trace starts out going through some splash screen. We navigate through the menus. We go along. And somewhere in there was a bug. Did you see it? Well, there wasn't actually a bug because Eric fixed it. So when I replay now, the bug isn't there. So I'm going to do a little smoke and mirrors for this next part because replays don't show the bug. But with the operation we can perform now is we say API trace trim -- frames equals 232, and it's plural because you could do like 232 - 235, 238, whatever. You have these complicated call sets of the things that you're actually interested in holding on to, and it will trim the trace down to just those frames. So if we did that, no, I did that. I actually will still. This is not smoke and mirrors. I'm going to replay. There, that was a replay to trace that is just the one frame. We got rid of all the menus and all of that, and it shows this. And again, that's a real replay with current Mesa, so you can't see the bug. So now it's the smoke and mirrors. Now I'm just showing you a screenshot of something like what the bug looked like. I didn't fake it very well. I looked and I couldn't find it in my hard drive, and I tried to log into my backups today at home. I logged into the machine at home, and there's input-output errors. I think my backup drive just died. Oh well. Hopefully I'll be able to resurrect that before this hard drive dies. Anyway, so let's look at the scroll bar here. We've got the top half of the scroll bar is there, and the bottom half of it is just gone for some reason. And that's not very. That's something like what the bug was. But you can see wow, what was that? I don't know what feature that was, Pippin. Whew. Okay, so you can see there's a lot of other things that are drawn. In this little thing, if I remember, I don't think this is sort of a screenshot. I think this is actually rendering a bunch of 3D stuff in sort of a scaled down mode. You know, and then it's drawing all these little widgets and buttons and these clouds. So Eric had been looking at this for a while. Days. And he knew the scroll bar was wrong, and he had tried and tried and tried. And he's one of the best at this job, to find obscure bugs and fix them fast. And he couldn't find it. He was ready to give up. He said, I can't find what's going on. I mean, this trace had like 500,000 OpenGL calls in it. And when we turned it down to one frame, now it has 100,000, but it's still a lot of different drawing operations, and most of them don't matter. Well, I spent some time, and I at the time, the drawing tool was kind of painful to use, had to kind of manually bisect, and I got down to a trace that gave Eric that. I said, here, play this trace and see if that helps. Within 1 hour, Eric had the commit ready that fixed the bug. So I learned we have the quality of our bug reports makes a huge difference, right? I mean, if someone said, hey, never winter nights, sometimes the scroll bar looks funky, Eric probably never would have touched it. Once we had a trace, he said, oh, look, I can find it. I can see the bug, spent a few days on it, still can fix it. But once we had a bug report that said, look, there's like 50 drawing operations here, and one of them's doing the wrong thing, he had it fixed in an hour. So bug report quality matters, and if we have tools that help improve bug report quality, those can be valuable. And that's sort of a general lesson that if you never use API trace and don't think it's interesting at all, and you wonder why anyone would use OpenGL, here's something I hope you can take from the talk that's generalizable. Tools that help you improve the quality of your bug reports make your developers a lot more efficient. They can find the bugs and fix them. So that was the first use case, was actually helping people send us good bug reports that capture what they actually care about. Second, I want to talk about debugging an OpenGL application itself. So there's a GUI thing for API trace, which has the unimaginative name of QAPI trace because it's implemented with a Q toolkit. Let's bring it up here. Oh, file trace doesn't exist. None of this is working. It all worked so well before. I think what happened is I ran the entire slideshow from the wrong directory or something. Anyway. You can all be bored while I stall and type this. So. Where is it? I don't even know where it ended up. I might have to generate a new one real quick. Okay. It is here. Okay. Okay, so here is the, thank you. Here's the API trace GUI that's coming up. It gives us a list of all the frames, and each one of these frames we can expand and see the calls. We can actually, from within the GUI, no, nothing is working. Wow, demo demons are hitting bad today. So, I'm going to come back to that. We'll give one more attempt at demos, and then we're just going to talk. Okay. Why is the menu is going up off the screen? Something changed with the projector. Okay. Anyway, you can see in here all of the in this application. So this is a very simple application. This is an application that I wrote. And you know it has to be simple because I don't know anything about OpenGL. One frame in particular draws, it sets the color, it sets the clear color and then clears. So it's drawing the screen to a solid color. And one of the things we can do is we can query and say, hey, what is the state at this point of the trace of everything about OpenGL? We can look and find what the state of the frame buffers are. We can say we've got a cyan background right now. We can actually take these calls and, no, I can't use the menu. See if I can get at it this way. Nope. So if my program were operating a little better, you can go in and change the parameters to any calls and actually replay it from within the GUI. So you can see what would happen if I changed this. And the demo was supposed to show you that I'd get a different color, pretty obviously. Okay. So if you have an OpenGL application and you can bring it up in the API Trace GUI, you can look at it and see what's going on. So there's some debugging you can do there.
I like these recaps columns.
Yeah, we're summary. It just reminds you what you've seen before. Okay. Conformance testing. We have what API Trace has a mode that you can run through, and this has, I think, been primarily useful for developers of an OpenGL implementation like us. That you can feed it a trace, and it will dump images for every frame of the trace out to a file, out to a directory, this reference directory. So then later we change our OpenGL implementation. We can then, so apparently the top of my screen is poison. If my mouse goes there, things go crazy. After we change our OpenGL implementation, we can run this dump again, and then it has a diff mode, and it goes through and does image comparisons of all the images. Our QA department has been using this, and they found that just doing the PNG encoding and decoding and comparison was taking a lot of time. So one of the tricks they came up with was to actually feed all of the frame buffer data back into the GPU, use the hardware video encoder, and get a video stream out the other end. And then they would compare these video streams instead. Or sometimes they're just comparing MD5 sums of the frame buffer. So those patches haven't been sent out publicly yet, but I'm looking forward to those. We could also do performance benchmarking. There's a lot of promise here if we could just take a bunch of really interesting applications and generate a trace for each one of them, and then that becomes our performance testing suite. And all we'd have to do to test things is loop over each of the traces and replay them and time how long it took. Well, that's hugely beneficial in one sense because it lets us avoid a lot of problems with the application. For example, Eric was debugging some performance problems in Minecraft. It's a popular application. A lot of people use it. And the only tool that Minecraft gives you to know anything about performance is you can turn on a little frames per second counter that shows up in the corner. And so he could watch the frames per second number, and it's going up and down and changing. Then he could go and he could change something in OpenGL, run it again, and the frames per second number is going up and down and changing. But he's in like this big 3D world environment, and there's random elements changing, and you could play single player, but you still have these randomized robots or whatever they call them that are coming to attack you. Meanwhile, you've also got this Java runtime environment that might be triggering a garbage collector, or it might be jitting your application so that you don't actually know what you're running at any one point. So if he was changing something that didn't have a large effect, it was often hidden in the noise of just running this application. Well, he switched to instead capturing a trace and then just replaying that trace. He didn't have to stare at the screen anymore to see the frames per second. He could just use time, API trace replay, and see how long it took. And suddenly, he has a reliable test case because all of the Java runtime is gone. We've just got this API trace program that's replaying it. So that reliability let him actually identify that his performance fixes worked. At the same time, not having the application around can cause some problems in our testing. We have, when the application and the OpenGL implementation are both running, there can be contention over cache lines and things like that. So now we've removed all that application logic. The cache behavior is not going to be exactly the same. So things are different. We also have added the API trace application. It's actually loading this file, it's decompressing it, and that ends up using up a lot of CPU and slowing things down. We've experimented with moving that to a separate, loading and decompression to a separate thread, and that helps. But we have one idea to completely eliminate API trace, the API trace runtime, by writing a mode that takes a trace file, dumps it out as a C program, and recompile it. So then we have a new native compiled thing that's just the OpenGL calls from the application, and all of the other application logic is gone and eliminated. So we think that's what's going to be our best option for a performance suite. We have some performance profiling inside the GUI. It runs through and can, for every call, time the CPU time and the GPU time. Both times are recorded using a timestamp that's exported from the GPU. We don't use get time of day or anything because we'd have two clocks and we'd never be able to keep them in sync. And And this is an old view of what it looks like. You can see here's a bunch of operations on the GPU. These down the side here we have a bunch of different shaders, and they're down below. They're the aggregate performance of the shaders. So you can find out here. This is usually the most important thing, which is the one shader that's using up the most time in this application, and then we know that's the one we want to go optimize inside our compiler. I spent a lot of time on the trimming code. It's a pretty hard problem to take a big trace of OpenGL calls and trim it down to a small number because there's these really hard to track dependencies. I have some code that's mostly working for that, and it's getting better. Finally, so things that we're working on now and that will be coming up in the future is faster and more robust trimming. This native compiled traces that I just talked about. We want to do some analysis of the profile data. Instead of just giving you that GUI view where you can look and see what happened, automatically identify, hey, wait a second, we submitted an operation on the CPU here, and then it appeared on the GPU there. Or we expected this operation to happen right before the VBlank, and instead, VBlank happened right after, and this got delayed an entire frame by the next VBlank. And those are some kinds of things that if you explored manually in the GUI, you might be able to see them, but we can do some automatic detection analysis of them. And then finally, on-demand tracing. I showed you that we can run an entire application and capture all of its data, but usually what you really want is one particular portion where the bug is or the thing that you're interested in. And wouldn't it be nice if you could run an application, just hit a hotkey at the time of interest and just capture a few frames? What's tricky about that is you won't have captured any of the setup that loads the shaders and loads the textures. So instead, you'd have to extract all of that out of the running OpenGL implementation. And being sure that you got everything reliably is tricky, but that should be a lot of fun. So finally, it's obviously an open source project. The website's there. We have a mailing list. You don't even have to subscribe first if you're interested. Or come talk to me. Like I said, our team's growing all the time. And if this sounds like some fun stuff to work on, come talk to us. Thank you very much.